Today's presentation will focus on accelerated biodegradation of chlorinated contaminants using in situ liquid activated carbon. With that, I'd like to introduce our presenter for today. We are pleased to have with us Mr. Matthew Valentine, Vice President and Project Manager at Woodard & Curran. Mr. Valentine has over 26 years of professional experience in geology, hydrogeology, and geotechnical engineering projects. For the past 16 years, he has managed a wide variety of projects ranging from environmental assessment and geotechnical investigations to feasibility and corrective measures studies. He has conducted, supervised, and managed subsurface explorations, remedial investigations, and site characterizations at numerous contaminated sites. We also have with us today Mr. Barry Poling, Central Regional Manager here at Regenesis. He has 15 years of experience in the environmental industry, including extensive experience in Phase 1 and Phase 2 site assessment, remediation, and industrial compliance. He provides senior leadership in the areas of remediation design, strategy, and business development. All right, that concludes our introduction, so now I'll hand things over to Matt to get us started.
Thanks, Dane. I appreciate the introduction and appreciate everyone for attending the webinar. This is a case study of a site that our company's been working on for over 20 years. We became involved in the site shortly after the RCRA facility assessment was completed in the early 90s. The first thing I'd like to go over is just an outline of the presentation and let you know that there'll be a project summary that I'm going to review, then a little bit about the site background, then a description of the site or the pilot study and the results of that pilot study, and then the remedial design that we went through with the help from Regenesis, the full-scale remedial action that we implemented, and some preliminary results that we found based on the initial performance monitoring that we've completed. So the project summary, the site is located in South Carolina. The stratigraphy consists of coastal plain sediments that are primarily composed of really anything from clay through sand and even some coarse sand units. The target zone for our remedial action is primarily comprised of a sandy clay, and it does have some sand stringers in it that created its own issues, and we'll talk about those later on. We conducted a remedial alternatives evaluation for the down gradient portion of the plume, which is going to be the focus of this talk, and we recommended accelerated biodegradation using PlumeStop, which is a liquid activated carbon. The pilot test was conducted using an injection of the carbon with a controlled release electron donor, which is HRC, and I think most of you folks have heard of that before. We also injected a bioaugmentation culture known as BDI to help enhance the reductive dechlorination process. The pilot test results demonstrated that the CVOCs decreased the concentrations in 2 wells from 98.7% to 100%. Based on the pilot test results, we went through a full-scale remedial design and then implemented that design using injection barriers. And for that full-scale implementation, the performance monitoring is ongoing. So a little bit about the background of the site. It's a former manufacturing facility that began operations in the 1950s, and actually it was a different type of manufacturing that started back way in the 1930s. The RCRA facility assessment was completed in 1989, and it identified 44 different SHMUs and 3 areas of concern. The RCRA consent order was issued in 1998, which prompted the RFI work to begin. We completed the RFI in 2007 and submitted the report to the agencies, and then that report was ultimately approved in 2010. Just wanted to highlight the site plan for everyone and to show that the general area of the plant itself, you're not intended to read every little point or every little word on this slide, but the general area of the plant is about 60 acres, and to the northeast is a landfill area that's also part of the site. Our focus is down here in AOC1, and this will be what we're going to focus on for this property or for this presentation, and the area down gradient of AOC1. Continuing on with the background, we conducted several rounds of source area treatment. In 2010, we did a nanoscale zero-valent iron injection and pilot test. And that test and application had limited success, so we continued to do work at the site, and in 2014, we did another full-scale application using 3DME, HRC, and BDI. And we're still in the process of evaluating those results, but the preliminary results look pretty good. In 2014, we conducted the remedial alternatives evaluation for the down gradient area. And in late 2014, we conducted the pilot tests that we're going to be talking about. In 2015, we completed the remedial design based on the successful results of the pilot test, with a goal to reduce contaminant concentrations within the down gradient plume and limit further migration of that plume. In late 2015 and January 2016, we implemented the full-scale design of the remedy. So next, I just kind of wanted to go through the conceptual site model of the site itself. Here's an aerial view of the site, and you can see the plant itself, the landfill area to the northeast, and what we'll show here is so that's the facility. The source area is actually a degreasing unit that was found in the building here, and this is really what defines AOC1. The plume we found extends about 1,700 feet from that source area down through in basically fields. There's a railroad here, and what we found throughout all of our investigations was the groundwater flow through this area averages about 60 feet per year, with a contaminant transport velocity of about 30 feet per year, or half of that. One of the interesting features of the site is immediately down gradient of the plume, there is a small residential area. Everyone in that residential area is on public water, and the city itself does have an ordinance for groundwater use. They're not allowed to use groundwater. They're required to be hooked up to the municipal supply. Okay, next I wanted to show a cross-section through AOC1. To the left, the northwest, this would be the source area, and then groundwater flow is also from the left to the right. There are 3 units of interest at the site. Unit 1 consists primarily of silts and sands, and it extends from about 5 feet below the ground surface down to 20 feet. The average horizontal hydraulic conductivity of that unit is about 5 to 6 feet per day, and there is a very strong downward vertical gradient. Unit 2, which is present about 25 to 45 feet below the ground surface, as you can see here, and you're not intended, again, to read all of the notes on this section. I just wanted to show that the sediments are basically flat-lying, and generally this is the zone that we're interested in. That zone is primarily composed of a sandy clay unit with sand stringers, as I mentioned previously. The average horizontal hydraulic conductivity of that unit is lower. It's only about 2 to 3 feet per day, and in that unit there's only a slight downward vertical gradient. But as I mentioned, about 90% of the contaminant mass is found in this unit. We also have a unit 4 present from about 60 to 80 feet below the ground surface. That consists primarily of fine sands that are partially cemented. The average hydraulic conductivity horizontally is 3 to 4 feet per day in that unit. And you might ask yourself, where's Unit 3? Well, there is no Unit 3 in this portion of the site. Unit 3 is a discontinuous shell hash unit that just isn't present in AOC1, but it is present throughout the rest of the site. Next, I wanted to go through some of the pre-remedial design work that we did. This just shows, actually, it's broken into two slides. This shows the cross-section that I just showed, and the green lines located here and here represent 2 of the 5 delineation boring transects that we did. We completed prepared a work plan that described this work, submitted it to the agencies for review and approval. Let me go back one second. Sorry. Okay. Each of the green lines represent delineation borings that we did across the transect of the plume. We collected both soil and groundwater samples continuously. The borings themselves were about on a 50-foot spacing. They helped really to delineate the width of the plume. So this is a continuation of that same zone. This is what defines the down gradient area, and we did 3 additional transects across the plume. The results of the pre-remedial design investigation helped us locate additional wells that we installed, and these wells are used for performance monitoring. It helped us update the conceptual site model, particularly with plume width and plume length, and it also served as a basis for recommending the pilot studies that we have completed. This slide shows the entire site in a colored contour map. You can see the source area is pretty obvious here. This shows the work before we did the source area treatment. What I'd like for you to pay attention to is the red box down here. This is where we focused our pilot study. And in 2 wells in particular, well BL55 represented a mid-plume location that had total CVOC concentrations anywhere from 6 to 12 ppm. The next location that we did our pilot test was BL59, and this was near the edge of the plume, the leading edge, and concentrations of CVOCs at that location varied from about 10 to 20 parts per billion. So I just wanted to show a general view of what the area looks like. Previously, it looked a lot like the background where we had forested land, but about 2 to 3 years before we did our work in this area, they clear-cut the area, and you can see what was left. It did create many issues when it came to access, and there are some areas that we'll talk about later further down that became quite swampy. This slide shows a blow-up of each of the 2 pilot study areas, the first being BL55, where we had higher concentrations once again. And in that location, we used 10 injection points. We injected just under 1,900 gallons of PlumeStop, 300 pounds of HRC, and 9 liters of BDI. And you can see the general orientation of the borings and how they were laid out. Down near the leading edge of the plume at BL59, 12 injection points were used, a little over 1,900 gallons of PlumeStop, again 300 pounds of HRC, and 9 liters of BDI. With that, I want to hand it over to Barry Poling. He's going to tell you a little bit about what PlumeStop is and some of the other work that they did during the pilot test that really helped to for its success. Barry?
All right. Thanks, Matt. So what is PlumeStop? I'm going to give you a short answer to this question, but if you're attending this webinar and you have attended some of our webinars in the past, we've went into some pretty extensive detail about the development of this technology, the results, and where we currently are. If you haven't seen those webinars, they are available on our website, so we can provide you, which will provide you with a much broader explanation. So, generally speaking, PlumeStop is a bioremediation technology designed to rapidly achieve low groundwater remedial targets and to show sustained reductions. The designed intent of this technology was to develop a flowable, dispersible sorbent that could be injected into the ground, and to sorb contaminants to it, but allow those contaminants to remain bioavailable for degradation. We looked at a lot of different things, including activated carbon, which is the class of technology that we keyed in on. Looked at powdered activated carbon. The challenge with powdered activated carbon by itself was that it's not flowable and it's very difficult to get into the subsurface. If you go back to what Matt showed earlier, this is a sandy clay site, sick plume, big area. The idea of injecting the powdered activated carbon into a plume like that is just, the logistics, it's challenging. So with that came the development of PlumeStop. And with PlumeStop, what we did is took powdered activated carbon and we mill it down to about 1 to 2 microns in size. So to put that into perspective, 1 to 2 microns is about the same size as bacteria or clay particles. That carbon is then suspended in a proprietary organic polymer, which creates what the tagline is, which is a liquid activated carbon. It looks a lot like what you see in this image, and it's flowable. It can be injected under low pressures. At this particular site, we were averaging under 30 psi across the entire area, so that gives you a sense of what we were able to do in a clay sand formation. If you want to go to the next slide, Matt, we'll talk a little bit about some of the strategy and our involvement out there. So, Matt mentioned earlier about pre-remedial design investigation. He showed some information on that. They did some extensive analysis to answer a couple questions. The first question was, how thick is this plume? The early investigation said it was 20 foot thick and it was 1,700 feet long. The question going into it was, is it really 20 foot thick? And in their pre-remedial design investigation, they looked at that on a macro scale and determined that it was. When we came into our pilot test, we wanted to go in, hone in on a macro scale and see if our investigation correlated with their pre-remedial design investigation within the specific pilot test treatment area. And to do that design verification, as we like to call it, we did two things. First, we did continuous soil cores with the goal of trying to identify mass flux zones. Okay. And as part of that, as part of the mass flux zone identification, we did analytical sampling, vertical profile sampling on about a 1 foot interval. And then we also did what we like to call settling tubes. Settling tubes are used to assist in determining the percentage of fines and coarse material particles within a particular sample. And then we're also looking at sand sizes and sortings. And on this next slide, you'll see some specific samples collected from within this treatment zone. These samples range from 24 feet to 27 feet. And really what we're looking for here is mass flux zones. We're trying to see on a micro scale, are there areas that have more sand than others? Are there areas with more clays than others? And then we go back and correlate that with the vertical profile sampling that we've done to see if, is it truly, to answer that beginning question, is it truly 20 foot thick? So the result of our efforts was that it correlated with the pre-remedial design investigation. The plume was truly 20 foot thick, and there were many micro fractures and small sand stringers that were discontinuous throughout the zone, which served as the transport zones within the aquifer.
Okay, thank you, Barry. I think one of the interesting parts of this project were the areas in which we were working. As I showed earlier, what the landscape looked like. Our first pilot test area was, again, around a well called BL59 It's actually located behind the truck, and it's located right off of a roadway. So the access for this location was actually very good. We had no issues with access. and all of that changed when we moved to our second location. But moving on, the weather was good during this event. We collected baseline concentrations of baseline samples, and what we found at the first location, the baseline concentrations were on the order of about 12 ppm of TCE. We conducted the pilot test and collected performance monitoring samples. 6 months post-injection of the pilot test, the TCE was completely degraded. The only thing left was Cis-1,2 DCE at a concentration of 375 ppb. After 12 months, we saw the Cis bump up a little bit, up to about 1100 ppb, and we'll be talking a little bit further about that later. But the overall results were 97 and 90% reductions of the total CVOCs at this location in 6 and 12 months respectively. The other things we noted were the indicator parameters were very positive in indicating that the degradation process was ongoing. This next slide just shows a graphical depiction of that. You could see starting back in 2012 when we first put this well in, we collected samples and it was basically a migrating plume, and you could see the increasing concentrations before we did our pilot test. The green line represents the pilot test injections, and you can see what happened within 1 month. The concentrations dropped dramatically. After 6 months, as we mentioned, we had 375 ppb of Cis-1,2 and then 1100 after approximately 1 year. You can see here also the blue represents the TCE concentrations and the red represents the total CVOCs, which in this case is primarily Cis-1,2. Then we moved down to BL59. Right before we moved down to this location, we got about 3 to 4 inches of rain, of course, and making access to this location next to impossible. Fortunately, we worked with our drilling contractor and the Regenesis field folks, and they were terrific in implementing the pilot. We ended up using timber mats after trying several different ways to access the area. The timber mats proved to be the most successful way of getting to these locations. The baseline concentrations at BL59, as you can see, we did have a little bit of Cis-1,2 DCE, about 9 ppb, and the TCE was around 12 ppb, much lower, representing the leading edge of the plume. After we did the injections, the performance monitoring results after 1 month showed non-detect of all CVOCs, which was sustained through 12 months, or 100% reduction of the CVOCs. The indicator parameters at this location were close to the baseline concentrations, and we didn't see much change in that, but that's likely due to the fact that the initial CVOC concentrations were so low at this location. Once again, here's another graph just showing what we're discussing graphically. So you can see the concentrations, total CVOCs up over 20. We did our injections, they dropped down to ND, and they sustained that for over a year. So based on those results, I wanted to go through the concentrations in a graphical format, on a tabular format so that you can see it. And Barry wanted to run through one of the notations that we saw as far as the results of the CVOCs, and particularly the Cis-1,2 at the BL55 location. Barry?
Yeah, thanks, Matt. So, really this is the goal of this is to predict a question that may arise, which is, what about the Cis production? Couple main points I want to make. First off, from a biodegradation standpoint, this is a reductive dechlorination project. We put in HRC, we put in BDI, and we are promoting reductive dechlorination through this process. And to add to that, a couple weeks ago we did another webinar which was on reductive dechlorination and ERD, and we we did a multi-site review, and we were trying to establish some trends, see what's expected at an ERD site. A couple of things that we noticed in that evaluation of the data is that, on average, we're seeing about a 2 to 3x increase with peak cyst concentrations as compared to your parent product, either PCE or TCE. So for instance, if you have 10 ppm TCE, you would expect up to a 20 to 30 ppm of cysts at peak. And that peak cyst formation, in our data has been hitting between 6 months and 1 year. So we're right in that wheelhouse from a timing perspective. But what you don't see at this site is cysts 2 to 3 times greater than TCE. So while we are seeing some cyst production, it's very muted compared to what we would expect under a traditional ERD. The reason for that is the PlumeStop, and that the degradation process is occurring. PlumeStop's making it more efficient. And, I always tell clients that if you think about it, that ERD is occurring under the veil of PlumeStop. You're just not seeing everything in the water. And, my colleague always likes to say that this peak is, think Alleghenies and not Himalayas, and that we're seeing much smaller, much shorter peaks with PlumeStop promoted ERD projects.
Thanks, Barry. So moving on, after the success of the pilot test, we conducted remedial design. And what the design consisted of was 3 injection barriers that transect the plume at varying distances from the source. Each of these barriers was 400 feet long. And we worked with Regenesis to determine many things as far as the design goes, but particularly the injection point spacing, the dosage amounts, and the product volumes. And honestly, we have to say that working with Regenesis was a very great process. They really showed their worth during this phase of the investigation. And we'll get into a little bit more detail about the design here shortly. We also worked with the off-site landowners on access issues. After our experience at BL59, we realized that we were going to only be able to access that area if we were to build a road through to get down to the 3rd barrier, which I'll show you here shortly. It was through a swamp, and that was no easy process. It ended up taking us quite a bit longer just to get the road in than we had originally anticipated. We discussed this approach with the regulatory agencies and submitted a remedial action work plan, which they reviewed and approved. Therefore, we proceeded implementing the work plan, and that work was just conducted from November of 2015, and we completed the full-scale application in January of 2016. Here's a picture of the full-scale design as we had originally laid it out. You can see the plume and the contours that make up the plume, again, the source area, and the 3 transect barriers that we designed, one near the leading edge of the plume, one mid-plume, and one about 300 feet downgrading of the source area. I'll show a blow-up of each of those sections now. Barrier design 1, which is the one closest to the source area, consisted of 59 injection points, 21,000 gallons of PlumeStop, 270 gallons of HRC, and 48 liters of BDI. It included a single row of injection points across the entire width of the plume, and then a second row of points throughout the core of the plume. And there were different dosage amounts and product volumes that were injected in these 2 different barrier rows. The mid-plume barrier, or barrier 2, was also 400 feet long. It consisted of 50 injection points, 22,000 gallons of PlumeStop, 180 gallons of HRC, and 40 liters of BDI. And it was a very similar design as the first barrier where we had one single row of injection points across the entire width of the plume and a second row of injection points throughout the core or this area. The third barrier was a little different than the first two. The concentrations are obviously much lower. It again extends 400 feet across the plume. It had 50 injection points, 10,000 gallons of PlumeStop, 100 gallons of HRC, and no BDI was injected along these points. The reason for that was that we saw some degradation of the TCE down at this location. We did see some Cis 1, 2, and that was really the first place we saw that throughout the entire plume. That may be related to the fact that it's located in a swamp, and the swamp may be providing some recharge that has higher TOC values than what we saw further up gradient. This is a slide showing the completed remedial action. What I'd like to draw your attention to is the blow-ups of each of the three areas. This first one was the one closest to the site, or barrier area 1, again mid-plume barrier area 2, and leading edge plume barrier area 3, and you can see the roads that we installed to access those areas. We did have challenges, two in particular for this remedial action. First, obviously, as we've been talking, the swampy timbered area and just getting access down to barrier area 3. That added a significant amount of time. The second challenge that we weren't expecting was the difficulty that we had in product delivery at barrier area 1. We started at barrier area 3 and completed those injections and barrier area 2 without really any problem injecting the required volumes into those injection points. We got to barrier area 1, we were able to inject into the core of the plume, but then as we moved out further to the flanks of the plume, it became much harder, and there were fewer sand stringers, which required us to inject more volume into fewer points in this location. And you can see on the blow-up, there are fewer points, particularly on the west end of this plume, on the west end of this barrier. The other thing I'd like you to pay attention to are the three wells that we're going to use and talk about to evaluate the performance of the remediation in the three areas. The most upgradient barrier, we're going to be looking at BL22, the second barrier area, BL62, and the third barrier area, BL59. We conducted performance monitoring. We've completed the 3- and 6-month events, and there's a 1-month post-injection event that's planned for January of 2017. Again, the three wells that we're going to look at and talk about here, BL22, 62, and 59, and the reason we're looking at those particular wells are because they are located in what we consider to be the zone of influence of the injections. Other wells, based on the groundwater flow, which is very slow, aren't really representative of what's going on or the result of the injections. So looking at BL22, we started with an initial concentration of almost 17 ppm, and you can see that breakdown. And then after 3 months, all that was left was 448 ppb of TCE and no daughter products. That's a 97% reduction in 3 months. After 6 months, all the TCE was gone. We had very low concentrations of some of the daughter products and 98% reduction after 6 months. BL62 is located on one of the flanks and not in the core of the plume near the second barrier, so we had lower initial starting CVOC concentrations. After 3 months, again, everything was destroyed, 100% reduction, and then those reductions persisted at 12 months after post-injection. BL59 was one of our pilot study wells. Sorry about that. And it, our initial concentrations were low because we had conducted the pilot test there. And basically what we were doing here is just showing that 21 months post-injection of the pilot, we still were able to sustain 100% reduction of the CVOCs. The other thing to note was many of the indicator parameters showed positive signs of ongoing degradation. So just summarizing what we've talked about so far, PlumeStop was used in both pilot test and full-scale applications at this site to treat the down gradient portion of the long, narrow CVOC plume, 1,700 feet. The pilot test results indicated a very rapid and sustained degradation of the CVOCs in groundwater. The post-injection performance monitoring of the pilot resulted in 90 to 100% reduction of CVOCs, and the concentrations of those CVOCs were fairly significant in mid-plume. Based on the success of the pilot tests, PlumeStop was also used in the full-scale implementation, utilizing 3 injection barriers that were 400 feet long each. Preliminary performance monitoring that was conducted as part of the full-scale implementation indicated contaminant concentration reductions of 98 and 100% for the wells that were located within the zone of influence of the injections. The indicator parameters are again showing positive signs that that degradation process is ongoing. One year performance monitoring event will be taking place in January, and we will allow for evaluation of the remedial progress of the injections at other locations that are further down gradient of the injection area. That concludes this portion of our presentation, and we are more than happy to go through questions. Barry?
All right. Thanks, Matt. So let's see here. I'm going to walk through a few questions that have been posted. The first few questions are just project related. Did you have any problems getting regulatory approval with PlumeStop in the state of South Carolina?
We did not. They were very receptive to just about everything we did, and in particular, the UIC process went very smooth, and they were extremely easy to work with and had no issues.
Okay, good. For the injection, did you use injection wells or injection points? Or direct push?
Yeah, for the pilot? Is that what you mean?
For pilot and full scale. Yep.
Yes, we use direct push. We use those. We did consider using injection points, permanent injection points, but in this environment, it's just as easy to go in with a DPT, and it turned out to be very successful.
Okay. I know you hit on this earlier, Matt, but I see a couple questions here. So is the source area being addressed, and if so, with what, and how's it going?
Yeah, I did touch on that originally. Back in 2010, we had done a fair bit of work in the source area, which culminated in a pilot test using zero-valent iron. We injected in the pilot, and it showed positive results. So we implemented a full-scale injection using that product, and it was marginally successful. It did shrink the plume a little bit. We found out that additional work needed done, so in 2014, we contracted with Regenesis and used a combination of 3-DME, HRC, and BDI in a little larger treatment area that extended under the building, and that seemed to be quite successful. We're in the process of performance monitoring to evaluate those results, but what we're seeing to date is some contraction of the plume, particularly at the leading edge and along the sides of the treatment zone, which is what we're expecting. So those wells in the source area will also be included in the January 2017 sampling event, and we'll be able to further evaluate the performance of that work.
Okay, great. Is the down gradient residential area concerned for vapor intrusion?
It's not, and the reason being our unit that we're most concerned with, well, first of all, the plume's not there yet. It is a concern. I mean, it would be a concern had the plume continued to migrate. But what we have is our zone of concern is located from 25 to 45 feet below the ground surface, and as I mentioned when we were looking at that cross-section, there is a zone of cleaner water in Unit 1 that extends from 5 to 25 feet below the ground surface, so that keeps vapor intrusion from becoming an issue.
Okay, Okay, and how long did the full-scale application take to implement?
It took a little over 2 months to complete. I believe we probably could have knocked 2 weeks off of that time frame had we not had the access issues we had, particularly at barrier 3, and then I'd say we had some additional delays related to the injection problems that we encountered barrier 1 when we were having difficulty injecting the product into the tighter clay in that portion of the formation.
Okay, and in the low-lying swampy area, what types of special actions were needed to work in there?
Well, yeah, we talked about that, and I got to show some nice pictures of what we were dealing with. So initially, when we were doing the pilot and we encountered what became a huge swamp, we tried many things. We tried bringing in gravel with geotextile, plywood, many different things, and what we ultimately found that worked was just the use of timber mats. So it did extend the amount of time, but once we were able to get the mats and procure them and move them around, it ended up being that's what we used. And then for the full scale, we, knowing what we learned from the pilot, we knew we had to put a road in, and that's what we ultimately did. And then that made it much simpler to get to the locations.
Okay, and a continuation of that someone asked was this a swamp or a wetland? Were there any wetland issues or regulatory issues you had to deal with?
There weren't, and it's only a swampy area because it does dry out, most of the year. It's just when you get large rain events, it drains. I mean, it lays there, but it takes a little bit of time to drain, but ultimately it does dry out.
Okay, good. Okay, I touched on this one. What injection pressures were you experiencing during the work? So I'll take that one. Generally, we were less than 30 psi throughout the majority of the project. Had a couple areas where we peaked up over that at certain depth intervals, but it was very intermittent. So generally speaking, less than 30 psi. So you mentioned that you had some trouble injecting at barrier 1. What sort of trouble, and how'd you work around that?
Well, that goes on to your pressure injection pressures that we had. They were significantly higher in barrier area 1, and we attributed that to just the fact that there were fewer sand stringers that were there to accept the product as we were injecting. It was interesting, after our experience at barriers 2 and 3, where we had no problems at all. We weren't expecting it, and we got up to barrier area 1 and just encountered this tighter formation. And so with the use of higher injection pressures, we were able to inject the product that was required at each of the areas, that being the core and then the outer portions and the flanks of the plume. On that western side, as we showed, we weren't able to get all of the points in, so what we ended up doing was injecting, say, double the volume and maybe half the points that were required. So we did get all the volume in, it just wasn't in each of the points that we had originally planned on.
Okay, good. Okay, this question's for me, and that I noted that CIS production was lower with PlumeStop than ERD, but it was still increasing as of the last data point. What do we think's occurring here? As I mentioned, in most of our data, we're seeing peak CIS and vinyl concentrations at 6 months to a year post-injection. So is there the potential that it could go up a little bit from where it's currently at 1 ppm? I think that could occur, but we're close to that number. I really feel like we've reached our peak levels and that we're going to start to see it going down. And is that breakthrough or rebound? I wouldn't call it rebound. There is a mass transfer phenomenon with carbon in general, that there's a greater affinity to sorb TCE than there is CIS. So it's more, one thing to remember, this is a barrier, it's a pilot test, and there is up-gradient parent mass continuing to flux through. And so as it fluxes through and there's that equilibrium between sorption and degradation, you can see, we think that's why we're seeing the 1 ppm of CIS. But if it's a standard ERD approach, we would expect 20 ppm assist or more. So there's a lot on there, or it's being degraded rapidly. Another question that's for me, I've seen this question in many forms. It's vinyl chloride. Why haven't you seen vinyl chloride? You're correct that we haven't seen vinyl chloride at the site. We have seen ethene in a few of the samples at certain areas, so that is there. We are also seeing many, the geochemical parameters support reductive dechlorination. So we're confident with the fact that the end product is being developed and geochemistry is correct. We're seeing sulfate reduction, all those sorts of things you want to see. We're confident that we're seeing complete degradation. So the question, where is the vinyl chloride? There's two possible scenarios there. One, it's being degraded more rapidly than it is being released into the water, so you're not seeing it in the water. The other is that it's just sorbed onto the carbon, so it never actually releases from the carbon, and you go completely through that degradation process without seeing it. And we've seen that on other sites as well. Most of the PlumeStop ERD sites that I've reviewed, daughter product production is muted compared to ERD alone, yet the geochemistry looks very similar. All right. Okay, so were there any underground utility challenges at the site?
There were not. There is one sewer line that runs down through the area, but it wasn't in the area where we were doing our injections. So we, after having it defined and we had the local utility come out and confirm its location, we really didn't have any issues with that at all. Okay.
Okay, here's another good one, pH. What about the pH in the groundwater? And I'll take that one, Matt. In one of the earlier slides Matt showed, we did show some pH data. In one of the wells, we saw pH drop below 6. You know, and in our experience, biodegradation rates may slow significantly at a pH below 6. In this scenario, we believe that the pH drop was temporary and likely due to an influx of organic acids released from the HRC in that localized area, basically into the well. And we expect that to stabilize over time. We believe this because, again, if you look at the geochemistry, we have solid evidence to support the biodegradation is occurring and that your ratios to TCE and DCE and parent are there. So in this case, pH has not been a challenge thus far. All right, so I've got a good question, kind of a wrap-up question here for you, Matt. What's next for the project?
That is a good question. We consider the remedial action that was done in both the source area and the down gradient, at least the down gradient area, as being the final remedial action for the AOC1 plume. Obviously, we'll be evaluating the source area, and if additional work needs done there, that'll probably be the next thing that needs to be done. But on a site-wide basis, we're in the process of conducting a risk assessment for the entire site. And then depending on the results of that risk assessment, we may be conducting some form of limited corrective measures. We're actually in the process of evaluating that right now. And in the short term, we will be conducting some additional groundwater monitoring, probably on a quarterly basis for at least another year or two, to evaluate the success of the remedial action in AOC1. But we feel the rest of the site, the other two AOCs, and all of the other schmooze have been adequately addressed, and we expect them to move forward through the risk assessment, and we'll have to see what happens beyond that.
Okay, good. I see one final question here I think I can pick off really quick. I understand that the liquid activated carbon was injected via direct push. Could you inject it through permanent injection wells? It's a short answer, yes, you absolutely could, and we've done that. And typically it's a cost benefit, but yeah, short answer, yes, it can be injected through permanent injection wells.